So now I want to discuss the equilibria of weak base. Based on Bronsted-Lowry definition, a base means a species that accepts proton. Right? So to accept a proton, a base needs only a lone electron pair. Alright. Okay, let's examine the equilibrium system of a weak base B in general as it dissolves in water. Right? So in this case, you see B as a base, aqueous, put in water. So what happened? B accept proton from H2O. B accept proton from H2O. In this case, B has lone pair, at least one. So used to form bond with the H, alright, from H2O. Therefore, they form BH plus aqueous and leaving plus OH minus aqueous. Okay, so from here you can see hydroxide ion produced. Therefore, the solution now become basic since the hydroxide ion produced. Okay, this generation for base is described by equilibrium expression below. Kc equal to concentration of BH plus times the concentration of OH minus divided by the concentration of P times with the concentration of H2O. So based on our earlier reasoning, so H2O we eliminate from the equation, means we negligible the concentration change. Therefore, Kb equal to concentration of BH plus times concentration of hydroxide ion divided by the concentration of B. Okay, despite the name of base dissociation constant, no base dissociate in the process. As you see, B base plus water. Okay, there's no dissociation on B. What dissociate actually? H2O. H2O dissociate to form OH minus, and one of the H, which is proton, donate to B. Alright. So we see base not dissociate. What dissociate is water. That's why we also can use base ionization constant. Base dissociation constant can be expressed as pKb value or by negative log the Kb. Alright. So pKb equal to negative log Kb. So if you want to get the Kb, that means anti-log, right? Shift log, then negative power of negative pKb value. Alright. So here Kb is directly proportional to the hydroxide ion concentration. Means if you have a stronger base means it has higher hydroxide ion, therefore you will have a larger Kb value. If we negative log the Kb, we get a lower pKb. In aqueous solution, the two largest class of weak base are first the molecular species of ammonia and the amines, to the anion of weak acid. Okay, this is example table 18.6 Kb values for some molecular amine base at 25 Celsius. Amine means they have N, right? N. Okay, for example, diethylamine here, you can see the reaction is as this one. You can see as the reaction occurs with water, water dissociate, and the diethylamine gains one proton, forming this compound plus OH. So Kb 8.6 times 10 negative 4, pKb 3.07. Alright, you can see my example here. Alright, as you see Kb go down here means Kb decreasing. Kb decreasing means basicity of the solution decrease. So Kb decrease, pKb increase. Right. Or we can say Kb increase, go upward, Kb increase, base strength increase, pKb decrease. Alright, opposite. Similar like Ka and pKa, right? Similar as pH and concentration of hydroxide ion. Okay, let me look at another example here. Sample problem 1811. Dimethylamine, CH3 and CH32 and H, a key intermediate in detergent manufacture, has a Kb value of 5.9 times 10 negative 4. What is the pH of 1.5 molar CH3 to NH? So the question now calculating the pH. To get the pH, you need to find the concentration of hydronium ion at equilibrium, correct? Okay. Okay, I simplify this discussion into PowerPoint. Alright, what is the pH of 1.5 molar dimethyl amine? Okay, plan. We start with balance equation. We need to start with the balance equation for the reaction of the amine with H2O, remembering that it is a weak base. Okay, so reaction with H2O, we write the balance equation. Then we write the expression for Kb. Right, from the balance equation, we can write the Kb expression. Then we set up a reaction table and solve for the hydroxide ion concentration. From the concentration of hydroxide ion, we can calculate the hydronium ion concentration and pH. Okay, we make similar assumption to those for weak acid. Actually, we have two assumptions here. First, since Kb is larger than Kw, the concentration of the ion from H2O is negligible. The auto-ionization of water. So the concentration of from the auto-ionization of water, the concentration of hydroxide ion is so small. Okay, another assumption that since Kb is small, we can assume that the amount of amine reacting is also small. That means the concentration of amine at equilibrium is almost equal to the concentration of amine at initial. Okay, solution. We write the equation first, balance equation. Okay, then we write the Kb expression from that. Okay. Then we have the reaction table. So we know the concentration is 1.5 molar at initial. So when this dissociation occurs, okay, at initial it is 0. The concentration is 0. Alright. OH 0. Alright. So change. Of course, it decreases by certain concentration. We put X. Alright. So negative X. So of course here increase by positive X, since stoichiometry is 1 to 1, so other side also plus X. So at equilibrium you get 1.5 minus X, right, for the amine, and then the ions X. Alright. Okay, now we make assumption to make calculation easier. We make assumption. Okay, but however, we need to check whether the assumption valid or not. How to check it? Easy. Take the initial concentration, divide by the Kb value. So if the Kb value, the answer here larger than 400, we can assume 1.5 minus X equal to 1.5, because X is small here, so small, therefore we can assume 1.5 minus X equal to 1.5. So calculate that, we put the value X squared divided by 1.5 equal to 5.9 times 10 negative 4. So we can solve the X equal to 3.0 times 10 negative 2 molar, which is the concentration of hydroxide ion. Therefore, from that, you can negative log the hydroxide ion concentration. You get 1.52. So to calculate the pH, you know, from the relation pH plus pOH equal to 14 at 25 Celsius. Therefore, pH equal to 14 minus 1.52, you get 12.48. That is the pH of the solution.